Hello, everyone. Welcome back. Today, we're going to be talking about characteristics of polynomial functions, and this entire unit, this unit 2, is all about polynomial functions. So, first, really quick, before we get started, I want to make sure we understand what is a polynomial versus what isn't. A polynomial can always be expressed in this way. A polynomial can be expressed as f of x equals ax to the power of n plus bx to the n minus 1 plus cx to the n minus 2, and so on, until we get to the very end, which is going to be look like maybe a1x plus b at the end, or b1, because these don't necessarily have to be the same number. So there we go. Now, many of these may just have zero. Many of these coefficients, a, b, and c, could just be zero, and so we don't actually have to have all the powers, all in a row like this in order for it to be a polynomial. Something else I should mention is the exponents must be members of the natural numbers. So if there's an equation with negative exponents, then it is not a polynomial. If there is an equation with half exponents, so for example 3 over 2, then it's not a polynomial. If you see the square root sign, it's not a polynomial, and so on. Okay, so a polynomial is either a linear equation or a quadratic or a degree 3 polynomial or degree 4 polynomial, degree 5, etc., all the way up until, pretty much as high as we want. In this course, we probably won't really be going past degree 5 polynomials, but technically a polynomial function can have any whole number degree, and that is okay. And just a quick review, what is the degree? Degree is the highest exponent we have on our x. So for example, this polynomial here has degree 4 because the highest power we have is 4, right? All linear equations have degree 1, right? Because all linear equations go with y equals mx plus b. And so the highest power on x is just x to the power of 1, right? For quadratics, the base quadratic is y equals ax squared plus bx plus c, right? It's just our basic standard form quadratic. And so all quadratics are degree 2 polynomials. So we're already really familiar with, quite a few polynomials. We're very familiar with lines by now, and hopefully also with quadratics by now. We're familiar with that from grade 10 and 11 content. So, that said, there are resources out there that I'd be happy to give if those are polynomials you're unfamiliar with, because with this course, we're going to go further. We're going to talk about degree 3, degree 4, and degree 5 polynomials, and a little bit beyond that as well. So, what are some key characteristics about polynomials? Or, in other words, anything that we can express in this form, what do we know about it? Well, we know that the domain is always R. So this actually mean all the real numbers. So the domain is all the real numbers, meaning that regardless of what our x value is, there is always a valid y value. And that makes sense, right? Is there any x value that I could put in here and we don't get a valid f of x? Well, no, there isn't, because we don't have any, over x, for example, right? Because if it was over x, then x being 0 wouldn't be possible, but this is not possible in our polynomials. Same with the square root sign. We can only have positives or zeros be in the square root sign. However, in polynomials, we're not allowed square roots, right? And so the things that generally make it so that we have restrictions aren't possible here. And so, therefore, the domain is just everything. As for the range, it really depends. It really depends on the polynomial. If it's an odd degreed polynomial, then the range would have to be, in general, for most odd degree polynomials, the range would be anything. It would be able to range throughout the entire thing. There are some exceptions, like for example, technically, if we had, a horizontal line, right, a line with no slope that's just y equals 5 or something, that would only range at 5, right? That wouldn't range throughout the whole thing. But other than, those a couple exceptions like that, generally speaking, all degree 3, degree 5, degree 7, all odd degree polynomials do range everything. Whereas even degreed polynomials, such as, quadratics and degree 4 polynomials, do have some sort of restriction on the range. We'll get more into that later, but I do want to note that the range isn't necessarily everything. And when it comes to even degreed polynomials, it can't really be, it can't be everything. It must have some restriction somewhere because the end behaviors are the same, which we'll get into later. I shouldn't get ahead of myself. Also, there are always no asymptotes, because what creates asymptotes? Well, we'll talk about that, but what creates asymptotes? Well, if we have a degree in our denominator and the degree in the numerator that are the same, then we would have an asymptote, right? However, that isn't possible here because we only have numerator degrees, so that's not going to happen. As for like vertical asymptotes, if we have certain values in our denominator of x that would give us 0 that don't cancel out with something on the top, that's also another way to get an asymptote. And so, but again, with there's no way to have over x minus 3 or something like this in the denominator of a polynomial, so there can't be any asymptotes. And so, long story short, with this, there is no possible way to have a polynomial with an asymptote. All polynomials have no asymptotes, right? No line ever has one, no quadratic ever has one, and no degree 3, 4, 5, etc. polynomial can ever have an asymptote. Then it says here, in a polynomial expression, the exponents on the variables must be whole numbers. So that's something we already covered. We already mentioned how we can't have a degree on a polynomial that is a fraction or something that's negative, because negative numbers can be like integers, -1, -2, -3, but they're not considered whole numbers. So the exponents for all the x's must be, or all the variables, I should say, all the variables, whether we're using x or we're using something else. Generally, we use x for polynomials, though. But anyways, generally for polynomials, we must have degree. We must have only zeros or whole numbers greater than 0 as our exponents. For example, here we could argue this is x to the power of 0, but as soon as we get to x to the power of -1, well, this is equal to 1 over x, and we can't have that. That doesn't count as a polynomial. Okay. The degree of a polynomial is equal to the highest possible exponent in the expression. Okay, so we already discussed that, how quadratics, because they have an x squared, they're degree 2 polynomials. Lines are a degree 1 polynomial in general, right? Whenever they go with y equals mx plus b, that kind of stuff, right? And so therefore, that kind of degree goes with the different type of polynomial there. And the last thing says, it just gives us kind of an example of that. It says, given f of x equals -3x to the power of 4 minus 2x plus 8, the degree of f of x is 4, and the leading coefficient is -3, right? So here's our leading coefficient, because that's the coefficient that goes with the highest degree, um, the highest degree part of the polynomial. So the degree of the polynomial is 4, because the highest exponent is 4, and the leading coefficient is the coefficient that is attached to the highest exponent, which is 4. Awesome, very good. All right, so now let's talk about something new, or something maybe that's new to a lot of you, which is end behaviors. So end behavior is basically what happens to the polynomial function eventually with respect to x and y. So how we would write our end behavior would be, as x approaches infinity, which means as our graph is going further and further and further and further to the right, what is happening to y? Y approaches what, right? Maybe y approaches infinity as well, right? So I'll give a quick example of that. Maybe y approaches infinity as well. In this example, that is certainly the case, right? Because as our x values are getting bigger, as we're moving further and further and further this way on our graph, our y values are also growing, right? They're also growing here. So maybe it approaches infinity. Now, maybe it approaches negative infinity. That's the other option. What if we have a graph like this, Well, now as x approaches infinity, right, as the x values are growing, 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 the y values are getting smaller and smaller and smaller. So we would be approaching negative infinity in that case. Now, I have another question. Is it possible to approach something that's not infinity or negative infinity? So, in general, yes, but when it comes to polynomials specifically, no. The end behaviors must be that as x approaches infinity, y either approaches infinity or negative infinity, meaning that it always goes there eventually. Now, I realize there's some cases where, certain like exponential functions or, that kind of thing, where this wouldn't be the case, but these are not exponential functions, keep in mind. We don't have a variable as an exponent. In this case, we have a polynomial, right? And so therefore it's not going to work. Although I realize I drew an absolute value, but let's just pretend it's a quadratic here that I had drawn like that. Same thing still stands with our quadratic, because I'm realizing technically absolute value I don't think would, that's going to be a piecewise function as opposed to a polynomial function. Although they do share a lot of the same characteristics, I find, with quadratics for sure. But anyhow, that's just it. It's not possible to have any other end behavior when it comes to polynomials. But of course, overall, with non-polynomials, it's not off limits for as x approaches infinity, y to approach a specific value like 0 or something like that. Okay. All right. So it's going to be plus infinity or minus infinity depending on the situation. And then same thing with as x approaches negative infinity. So as we get further and further left, are we going up, right? Are we approaching net infinity, or are we approaching negative infinity? So basically, long story short here is that we must look at the graph to determine. Okay, if we have a graph, the easiest way to find the end behavior is to just look at it and determine what the end behavior is. Now, let's say that there is no graph, that we're not given a graph, we're just asked to determine the end behavior, but we're not asked to also graph the function. Well, if that's the case, there is actually a shortcut for how to do this. So let's talk about that shortcut. So let's look at specifically linears and quadratics. So we're going to use linears as our degree 1 example. So its linear equations are degree 1 and they're odd, and they go with the equation y equals mx plus b. Y equals mx plus b can express the general form for a line. Now, when it comes to lines specifically, how would we know the end behavior? Let's just think about what we already know. So how would we express? We know that if m is greater than 0, then that means our end behavior would be as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y also approaches negative infinity too, right? Because if we just picture that, if we have a positive slope, then that means as x gets higher, y gets higher, and as x gets lower, y also gets lower and lower, right? And so that's the general thing. And here's the thing, this is true of all odd degree polynomials, right? So let's express that way. Actually, I'm going to write the rest of it for this one too, that if m is less than 0, then as x approaches infinity, y approaches negative infinity, so it's the opposite, right? The opposite is true. And also as x approaches negative infinity, y approaches positive infinity. So they've swapped here. Now let's make this infinity sign look a little bit better. Beautiful. Amazing. Okay. Now, this can actually be generalized, as I was saying before, to all odd polynomials. So for all odd polynomials, if the leading coefficient, so instead of m this time, we're going to say leading coefficient, if the leading coefficient is greater than 0, then we have the same pattern as before. We have as x approaches infinity, y approaches y approaches infinity, and as x approaches negative infinity, y approaches negative infinity as well, which is pretty good. Okay, and then same thing if the leading coefficient is less than 0, then as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches infinity. So it follows the same pattern for all odd degrees. So if we have a degree 3 polynomial and we know that the exponent, the leading coefficient is positive, the leading coefficient is positive on our degree 3 polynomial, we know this is our end behavior, right? Because our leading coefficient is greater than 0. If our leading coefficient is negative on a degree 3 or a degree 5, degree 7, whichever odd degree polynomial, we know this is our end behavior. And so that's the great thing about end behavior, is that what we observed about linear relations can be generalized to all odd degree relations, or polynomial relations, specifically polynomial functions. Okay, now let's grab a second page because I now want to talk about even degrees. For this one, we're going to first talk about quadratics. Okay, so for quadratics, what do we know? So for quadratics, we know that y is equal to ax squared plus bx plus c. And we know that if a, we know back from grade 10, from grade 11, that if a is positive, right? If a is positive, so if a is greater than 0, then the parabola opens up, right? That's what you were told, right? So if the parabola opens up like this, that means that whether x is approaching infinity, right, whether we're going further and further left or further and further right, where x is approaching positive infinity, whichever direction we're going, we're opening up. So y is always getting bigger and bigger and bigger, right? We have a minimum value down here somewhere, but we don't have a maximum value because sky's the limit. Well, really, infinity's the limit. So it would just continue to go up and up and up forever. And so in this case, as x approaches infinity, y also approaches infinity. And as x approaches negative infinity, y still approaches infinity, right? If we can picture any quadratic where it opens up, regardless of how far left we go or how far right we go, right? We're still going up. We're never coming back down because the minimum point is our vertex and we never go back down there again. Very good. Okay, excellent. Very good. Now, what do we know? Also, we know that if a is less than 0, if we have a negative a value, that means what about the parabola? That means the parabola opens down, right? Which means that as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y still approaches negative infinity. So either way, whether we're going far left or far right, we're just going further and further down. The farther right we go or the farther left we go, the further down we end up. Good. Now, what we're observing about quadratics, this can be generalized to all even degree polynomials, right? Because quadratics are degree 2, but this can be generalized to all even degree polynomials. So for all even degree polynomials, they're going to follow this pattern. Because in this case, we chose a because that's our leading coefficient. For all even degree polynomials, if the leading coefficient is greater than 0, then we have the same end behavior as this first one, whereas x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches infinity still, right? Because they go in the same direction. With even degrees, they both go up in the same direction. And that kind of goes back to something I mentioned earlier, where I was saying that an even degree polynomial isn't going to have a range of everything, whereas in most cases, an odd degree polynomial will range everything. Okay, very good. And then if the leading coefficient is less than 0, then as x approaches infinity, y approaches, sorry, this should look more clear. It's infinity, not negative infinity here. Negative infinity. And then as x approaches negative infinity, y still approaches negative infinity, right? So the parabola opens down, or, more broadly, the degree, you know, degree opens down. Awesome. Okay. So now let's go ahead and do some examples here. So let's take a look at this, at this equation and see what we're doing. So here we have our equation and our graph. Looks like we have a parabola. Our degree is clearly 2 because the highest power is 2, so that's going to be 2. Is it an even or odd degree? It's an even degree because 2 is an even number. Now, don't get even versus odd degree mixed up with even or odd function. Those are two totally different things. All we have to do for this part, it's not a trick question, it's just look at the degree, and if the degree is an even number, we write even. If the degree is odd, we write odd. Simple as that. Then we have our leading coefficient. So we actually just have an invisible 1 here as our leading coefficient, so it's just 1. Now 1 is a positive number, which means that as x approaches infinity, y also approaches infinity, and as x approaches negative infinity, y approaches positive infinity. Very good. Now, we can also view that from the graph. We can see that regardless how far right we go on our graph, we're always zooming up. And as regardless how far left on our graph we go, we're still zooming up. We're still going upwards. Then it asks, what are the number of turning points? The number of turning points is one turning point. And partly that's because we can see that on the graph. We can see there's one turning point. Now, in general, the maximum number of turning points there can be is 1 less than the degree. So since the degree is 2, the maximum turning points we can have is 1. And for quadratics, as we know, all quadratics do have just one turning point. What about for linear equations? They wouldn't have any turning points because it's just a straight line. For degree 3 polynomials, they can have up to 2 turning points. We have to look on the graph to decide that, but the maximum they could have would be 2. But that said, not all, most cubic functions, right? Most degree 3 polynomials do have exactly 2, but some don't quite have 2. Some might just have 1 or something. So do keep that in mind, that the turning points is not just always 1 less than the degree. However, it is usually exactly 1 less than the degree, but also 1 less than the degree is the maximum number of turning points we can have. And in general, that is the number we'll have, but not every single time. There are exceptions, so do keep that in mind. Awesome. How about this next one? This is a degree 4 polynomial. I see 4 as our leading coefficient here. That is also an even degree because 4 is an even number. Leading coefficient would be 3. I see 3 right there, so that's 3. Now that is a positive leading coefficient, right? That's a positive number. And this is an even function or an even degreed function as well, right? And so that means that as x approaches infinity and negative infinity, y approaches infinity for both times as well. And we can clearly see that here. We can clearly see y approaching infinity very quickly, much quicker than x approaching infinity, in fact, as well. Then it asks number of turning points, and since degree is 4, we know the maximum number of turning points would be 3, right? Maximum we have 3. And in this case, we do have 3. We have 1 here, and 1 here. So there are 3 turning points. Okay, let's try this one. This is a degree 6 polynomial. It is also even degreed. And in this case, the leading coefficient is 2, right? I see a 2 here right beside the x to the power of 6. And because 2 is also a positive number, and just looking at the graph here as well, we know the end behavior is that y approaches infinity as x approaches infinity and as x approaches negative infinity. And as for our number of turning points, the maximum would be one less than the degree, so maximum is 5. But let's count them to see if there actually are 5. There probably are. 1, 2, 3, 4, 5. So yes, there are 5 turning points, and I'm going to write down 5 right now. Very good. Okay, let's move on to this one. First, we have to write down what's the degree. So degree is 4. There we go. And then we have the degree as either even or odd. So in this case, the degree is even. So there we go. Now, what is the leading coefficient? Leading coefficient is a negative sign. So leading coefficient would be -1. Since it's negative, that means that as x approaches infinity and as x approaches negative infinity, y is approaching negative infinity for both. Let's be clear, it's negative infinity. And that also makes sense with our graph, right? We see both these arrows going down, downwards pretty quick. So clearly we're approaching negative infinity in both directions. And then the number of turning points. Well, it's a degree 4, so maximum would be 3 turning points. And there are indeed 1, 2, 3 turning points. So I'm going to write 3 there. Very good. Okay, let's try this one. Now we're getting into some odd degrees. So here we have degree 3 because the leading coefficient is a 3, right? X cubed. Is the degree even or odd? Well, 3 is an odd number, so I'm going to say it's odd. The leading coefficient, well, there's no number here, so that just means the leading coefficient is 1 if we see nothing. 1 is a positive number, and for odd degree functions, remember it works different than even degree functions. If we go over here, for any odd degree functions, as x approaches infinity, for any positive degree, any positive leading coefficient odd degree polynomials, that means as x approaches infinity, y also approaches infinity, and as x approaches negative infinity, so does y. That also lines up with the line, right? The linear function. So let's say we forgot which way around it was. Think about how the line works, and that's how this is going to work as well. Or also, in this case, we can look at the graph and kind of see that, oh, as x approaches infinity, y is also approaching infinity, much faster, in fact. And as x approaches negative infinity, right, as we're getting further and further left on our graph, we're also getting further and further down. So that's another way we can kind of verify the end behavior there. So there's a couple ways, which is always nice. So there we go. Then it asks the number of turning points. So we know the maximum would be 2 because degree is 3. And I do indeed see 2 turning points here. So I'm going to write down 2. Okay. Next, let's take a look at this polynomial. Looks like our degree is 5 because our highest exponent is 5. Looks like that is an odd degree, right? 5 is an odd number, so it's an odd degreed polynomial. The leading coefficient is 2. And because that leading coefficient is a positive number, that means that it will follow suit with the last one, that as x approaches negative infinity, y will also approach negative infinity. And as x approaches infinity, y approaches infinity. Awesome. Very good. Then they have the question here of the number of turning points. So of course, since the degree is 5, the maximum turning points we could possibly have is 4. And we do indeed have 4. 1, 2, 3, 4. So there we go. Awesome. All right. Now let's move on to the next one. This one is also degree 5. Okay. So for this one, the degree would be 5, right? Because we have x to the power of 5 right here. So degree is 5. That is an odd degree, right? 5 is an odd number, so it's odd. our leading coefficient is 5, which means that that's positive. So therefore, we're going to have it, as x approaches negative infinity, y also approaches negative infinity, which we can also tell from the graph too. And as x approaches infinity, y approaches infinity. Very good. Now, we know that the number of turning points, the maximum can be 4, right? Because it's degree 5. But in this case, I only see two turning points. And so we're going to write down 2. Now, even though I know this is the first one where the turning points hasn't been exactly 1 less than our degree, and in general, most of the time, the turning points are exactly 1 less than the degree, but there are some exceptions like this one here, and we'll talk about why there are exceptions and how we would know, without the graph, that there would be exceptions later on. But for today, we're just going to look at the graph and recognize, oh, there's only 2 turning points, and write down that there's only 2 rather than 3 or 4, because there normally would be 4 for a degree 5 polynomial. Very good. Okay, let's move on to this one here. Here we have a degree 3 polynomial. So let's put 3 for degree. And that is an odd degreed polynomial, so we'll put odd here. And then what is our leading coefficient? It's negative 2. Because that's a negative number, that means as x approaches infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches positive infinity. So it's opposites. And that's what it looks like on the graph too. It looks like as x is getting smaller, y is getting bigger really, really fast. And then as x is getting bigger, y is getting smaller pretty fast as well. As for turning points here, we know the maximum would be 2 turning points because it's degree 3. But in this case, I only see 1. I only see 1 turning point kind of around here where we kind of have a point of inflection there, which we'll talk about what that means later. But I only see 1 turning point rather than 2. And so the answer here, we'll just put 1 for the turning point. All right, well, that is everything for today. That's all of them. So good work today, everyone. And I will see you next day to keep talking about more polynomials. Bye, everyone.